Hi there, and welcome back. In this video, we will start to learn array data structure. It is the most used data structure. An array is a simple collection of objects or things. They are very powerful data structures that store list of elements and they have endless applications. Simple examples can be collection of books on our table, clothes in our wardrobe, and pens in our pen stand. Let's quickly examine one of these real-life array structures to understand the logic behind the array. So here we will look at this box of macarons. This box of macarons is very similar to array data structure. If we look at this box very carefully, we can easily see what properties of this box of macarons. Okay, first is it's a box of macarons which holds only macarons. This means that this box is produced for macarons. You cannot store, for example, cream puff in this box because it will not fit in. This box is produced only for storing macarons. The next property is that all macarons in this box are next to each other. There is no gap between them, which means that they are contiguous. The next property is each macaron over here can be identified uniquely based on their location. So let's say if we want to take this macaron over here, the location of this macaron is 1, 2, 3. So this is unique location for this. Then if we want to take this macaron from here, the location of this macaron will be 4. As you see, each of these macarons has its own location, which is unique. So the last property is that we cannot change the size of this box, which is fixed. This means that this box is produced by some standard manufacturer and assume that there will be only 10 macarons. We cannot change the size of this box, or we cannot put 11 macarons inside this box. It is produced by standard manufacturer to hold only 10 macarons. So these are the common properties of this box, and we can easily see them if we look at carefully. So if we compare this box of macarons with the array structure, we see that they are very similar. So a typical array structure looks like this. Here we have 6 elements. Here you can easily see that the appearance of macaron box and array structure somehow looks like each other. Now let's look at the properties of this array, and we will see that they are similar to the properties of this box over here. So the first property is that array can store data of specified type. This means that when we create an array of integers, we cannot store string values in this array. So if we try to insert this value to this array, it will raise error. We cannot do that. So as you see, this property is kind of similar to this property, the first property of this box. Here we can think that data type is macaron, so we cannot store this cream puff into this data because this is for macaron. So in array, the data type is integer. So if we want to store string value over here, it will raise an error and will not allow us to do so because this is how arrays work. Once you have defined the type of data for array, the elements must be the same type of the data that we defined. Okay, let's continue to the next property. The next property is elements of array are located in contiguous location in memory. This means that elements of array are next to each other. So there is no gap between them as we have in the macarons box. As you see, we don't have any gap here and we don't have any gap between these elements. They are located next to each other. So the next property is each element of array has a unique index. As we have here, we have unique locations for these macarons and we have unique indexes for each element of array. So if we want to access, for example, this element over here, we need to access through index of 2. And here take into account that indexes start from 0, not from 1. And their increases sequentially. So the last property is the size of array is predefined and cannot be modified. So here again, if you look at this box of macarons, we see that the size of this box is predefined. And this is applicable for array as well. When we create an array, we define its capacity. So we cannot change it later on. This is the biggest limitation on array. So this is all properties of array. As you see that it is somehow similar to the properties of this box over here. Hopefully you now have a picture of array, what it looks like. Now let's see what is the definition of an array in computer science. In computer science, an array is a data structure consists of a collection of elements, each identified by at least one array index or key. An array is stored such that the position of each element can be computed from its index by a mathematical formula. So here we have a collection of integers and each of them identified by array index. So based on these indexes, we can find any element and do any mathematical calculations on them. Now you might be interested, why do we need an array? So in software programs, the array is used almost everywhere in the program to store any data. Consider a situation where we need to store 3 integer numbers. If we use programming simple variable and data concept, we need 3 variables of integer and we can store our numbers in these variables. So we don't have any problem. It's very simple. Because we had to store just 3 integer numbers, so we don't have any problem. We can create 3 variables and store our 3 integers inside these variables. Here is okay. Now let's assume we have to store 500 integer numbers. Are we going to declare 500 variables? Of course not. So to handle such situation, almost all programming languages provide a concept called array. An array is a data structure which can store a fixed size collection of elements of the same data type. So instead of declaring 500 variables, we just need to declare an array with the type of integer, keep these variables inside array. Then later on, by using indexes of array, we can access these variables easily. And that's it. Hopefully, with this lecture, you have understood what's an array and why it's essential in programming. In this video, we will learn about lists. Lists are data structures can store multiple values. They are unique in how they pair data with pointers. The pointers indicating the next piece of data's memory location. In lists, data is stored in various disjointed locations in memory. Because the data is stored in different locations, each piece of data can only be accessed through the pointer that precedes it. Addition of data is performed simply by replacing the pointers on either side of addition. So if we want to add yellow color after the blue color, we just need to replace pointer from blue, which goes to green, to the yellow, and from yellow to green. It works like this. The pointer goes from yellow to green, and the pointer that goes from blue to green replaced to the yellow. And that's how the insertion works. The most prevalent type of list is linked list. A linked list is data structure that holds group of items which present a sequence. Here each data item is referred as a node. The node contains data and the link to the next node in the sequence, and they are interconnected with their links. More complex form of lists add additional links. The main advantage of linked list is quick insertion and deletion. Linked list is a linear data structure like arrays. There are 2 main types of linked list: single linked list and double linked list. In single linked list, each node has only reference to the next node. In double linked list, each node has reference to the previous and the next node, As you see in the picture, in double linked list, we have a connection to the next node and the connection from the next previous node. Begin and end of list can be tracked using pointers called head and trail. So that's it. In this video, we learned what is list and the logic behind addition in the list and main types of list. And we have also explored the most prevalent type of list, which is linked list, and the types of linked list. Stack. In this video, we are going to talk about stacks. Stack is a linear data structure which follows a particular order in which operations are performed. A stack is a last in, first out data structure. The structure of stack can be imagined as a pile of objects stacked vertically. As you see, when a new element comes in, it's placed on the top of previous one. When extracting these objects, the last one added to stack is the first one removed. That's why it's called last in, first out data structure. Stacks are similar to arrays, but with limited control. By using push method, a new element can be added to top of stack, and by using pop method, an element can be removed from the stack from the top. Here we will visualize how push and pop methods are working. When adding data to a stack, the data is put into lowest available location. And when extracting data from a stack, the most recently added data is removed first, as you see in the animation. This method of extracting the most recently added data first is called last in, first out, or LIFO for short. So where can we use stack data structure? There are many real-life applications which use stack efficiently, such as under-redo functionality, to reverse a word, backward-forward stacks on browsers, backtracking algorithms, and parenthesis checking. Okay, that's all for the stack now. Let's summarize what we have learned. Stacks are last in, first out data structure. Data structure of stack can be imagined as pile of objects stacked vertically. Push method can be used to add new elements to the top of stack, and by using pop method we can remove elements from the stack. There are many applications that are using stack data structure. Some examples of them are shown here. It's one under-redo functionality to reverse a word, backward-forward stacks on browser, backtracking algorithms, and parenthesis checking. A queue is a first-in, first-out data structure, which means first come, first serve. It's also known as waiting lines. As the name suggests, it can be easily imagined as a group of people waiting in line. Why would you need this? Well, in many algorithms, you want to add items to a temporary list at some point, then pull them out of this list again at a later time. Often the order in which you add and remove these items matters. In queues, the sooner a person lines up, the higher their priority. As I mentioned, the logic is first come, first serve. The term enqueue is referred to the act of adding element to a queue. When a new person comes, he stands at the end of line, conveniently adding the data to a queue. The data is placed at the end. So, as in real life queue, when an element is added, it's placed at the end. As you see, when we add new data, it stands at the end of the queue. When extracting data from the queue, the data has been in the queue the longest is removed first. The term the queue refers to the act of extracting data from queue. Visually, it will be like this. The first element that's added to the queue served first. That's why this data structure is called first in, first out, or FIFO for short. Where we can use this data structure. Real life example for queue usage can be point sale system of restaurant. It is obvious that the orders must be processed as the order they were received. As an order is received, it writes to the back of the queue and reads order from the front of the queue by cooker's device. This allows cookers to cook meals as the order they received. Let's summarize what we have learned. We know that a queue is first in first out data structure. The structure of queue can be imagined as a queue of the customer waiting at the cash desk. We can use enqueue term to insert to the queue and dequeue to remove an element from the queue. And the real life example can be point sales system of a restaurant. Hash tables. A hash table is a data structure or associative arrays that groups value in an index and sort and retrieve data using key-value mapping. It accomplishes the same goal in some cases like Swift dictionaries. However, the efficiency of hash tables are better than dictionaries. As mentioned, hash tables are good at sorting data in sets made of keys and values. As shown here, in this case, a name is a key and the value is sex of a person. As an example, let's imagine that the data in the diagram stored as an array. So we prepare 5 boxes for array and sort the data in them. Let's now imagine looking up Kate's sex. And we don't know the index for the Kate's box in the array, thus we need to search in order from beginning. This operation is called linear search. So the key for the data stored in box 0 was John, which is not Kate. Then we continue to box 1 to check, and this is not also Kate. And then we continue to box 2. Here we see that it's not Kate either. Finally, the key for the data stored in box 3 matched Kate. By extracting its corresponding value, we learn that Kate's sex is female. In this way, linear operation carries a cost proportional size of the data. The time complexity is O(n). This is resource and time consuming. So how to solve this problem? A hash table solves the problem of linear search operation, which is costly and time complexity is O(n). The time complexity for searching, inserting and deleting is on average O(1), which means that regardless of the size of the input operation, time remains constant. By calculating hash value, we can find the index and place the value in its index and retrieve the value based on it. A hash table consists of 2 parts, index and value. The index is computed sequence of numbers and characters, which is different from dictionaries. The process of creating a unique hash is called hash algorithm or hash function. This image illustrates that input of Swift always produces the hash result of 3. The values are stored in buckets and their position is computed by hash function. It's a function that can be used to map a data set of arbitrary size to a data set of fixed size, which falls into the hash table. Basically, what hash function is doing, it's calculating index value, and based on the index value that we get from hash function, we place our object in buckets. So every time an index value for specific element is same, which makes search, insert and deleting process very fast. As an example, let's prepare an array to store some data. For convenience, we have 5 boxes in the array. So let's store some data. When adding the data of John, we calculate a hash value for the key using hash function, and the result is 4928. Then it's divided by the number of boxes in the array, which is 5, to find the remainder. For this we are using mod operation, and the result from this operation is 3. So the data of John is stored in the box of 3 of the array to match the result. This operation will be repeated to store other data as well. Okay, when storing the data of Sue, we again find key's hash value and perform mod operation on it using the number of boxes in array, which is 5. And the result from this mode operation is 1. So the data will be stored in box 1. Next we'll store dense information. Again, by finding hash value and performing a mode operation on it, we find the result, which is 4. So the data goes to the box 4. Okay, there might be a question that what of the calculated value is equal to the one that is filled. Okay, I will show you how it works. Let's continue to add our data when adding the data of Nelly. Again, we are calculating hash value using hash function, and we perform mode operation, and we see that the result is 1. When trying to the box 1, we see that this is already filled. In box 1 we have shows information. If something like this happens, it gets connected to the existing data as a list. There are various types of hash table structures. The method that uses list in hash table is called chain method. Then we will continue to add the data of Kate by doing the same calculation. And we find out that this is 3. So the information will go to the box 3. So again, our box is filled with the data of John, so it will get connected to it. Finally, the last data we will add is the data of Eddie. Again, same calculation is done here, and the result from this function will be 3, which means that it will go to the box 3 and get connected to existing data as a list. So all data is finished being stored, and the hash table is complete. Next, we are going to search for information inside hash table to find out gender of inserted names. As mentioned above, hash table makes search faster. Let's find out Dan's gender and see how the process is working. In order to find box of Dan in the array, first we need to find the key's hash value and perform mode operation on it, using the array count, which is 5, and the result we see that is 4. So we can easily find the Dan's information in box 4. By extracting the corresponding value, we can identify Dan's gender. Okay, what happens if we look up for Kate's gender here? Again, in order to find box of Kate in the array, we find the key's hash value and perform mode operation. So the result is 3. So if we go to the box 3, you will see that the data stored in box 3 is, in this case, linear search is performed on the list started from the John and check all elements one by one. And when the Kate's information found, it will extract the corresponding value and we can identify the Kate's gender, which is female. As you can see, by using hash function, hash tables are able to quickly access the data within an array. When hash values overlap, lists are used. Finally, take into account that if the size of array used by a hash table is too small, the overlaps increase, which in turn makes linear search more prevalent. Conversely, if the array size is too large, there will be many boxes with no data in them, and this is wasting the memory, thus discretion is needed. Hash table applications. When we can use hash table? Due to the fact that time complexity is O1 for sorting and retrieving, it's ideal for databases where you have a growing set of data. When we cannot use hash table? It's not recommended to use a hash table where you have to iterate over large amount of data. Hash table mostly used for fast data lookup, database indexing, cache, and unique data. Heaps. Heaps is a special case of balanced binary tree data structure where the root node is compared with its children and arranged accordingly. Based on this criteria, a heap can be of two types. Minimum heap, where the value of root node is less than or equal to either of its children. And the second one is maximum heap, where the value of root node is greater than or equal to either of its children. Let's look minimum heap. And as a rule, here a child number is always greater than its parent. Okay, let's try to add a number to our heap. The number first is added on the end of the line. If the parent happens to be greater, in our case the parent is 6, which is greater than 5, then the child and parent swaps. This operation repeats until no additional swaps occur. The parent of 1 is less than the child 5, so which means that no additional swap occur. So the addition of number to the heap is now complete. When extracting a number from the heap, the number on the top is removed, which is the smallest value. Due to the top number is removed, the heap structure needs to be reorganized. The number at the end of line moves to the top, and when one of the child numbers is less than the parent, the lowest of adjacent child numbers swaps with the parent. So the parent is 6, which is greater than the right child, which is in turn greater than the last child to the left. So the left child and parent swap. In this way, heaps can be used. This operation repeats until no additional swaps occur. So we compare 6 with 4. We see that 6 is greater than 4, which means that the swap should be occurred. So the element reached the end of the line, so no additional swap will be occurred. So this is the end of extracting the data from the heaps. In this way, heaps can be used to quickly extract smallest data. However, extraction of data in the middle of the tree cannot be performed. Okay, where can we use heaps? Heaps are used in things like priority queues and Dicaster's algorithm. We will talk about Dicaster's algorithm in our next lectures. So to conclude, we know that there are two types of heaps, maximum heap and minimum heap, and we have learned how to add an element to the heap and how to extract an element from the heap. Binary search trees. A binary search tree is a binary tree in which each node has at most 2 children, and it facilitates fast search, insertion, and deletion operation. The time complexity of each operation is O log n, which is considerably faster than linear search. These kind of trees have two properties. All nodes are greater than the nodes in their left subtree. For example, the node 9 is greater than the other nodes in the left subtree. Likewise, node 15 is greater than other numbers in its left subtree. The second property is that all nodes are smaller than the nodes in their right subtree. For instance, node 15 is smaller than the other numbers in its right subtree. So, taking into account these properties, we can conclude that a binary search tree's smaller node is located at the end of leftmost tree here. Conversely, a binary search tree's largest node is located at the end of rightmost subtree, line stemming from the topmost node, which is 28 in our case. Let's look at the process of adding nodes to a binary search tree. As an example, we will try to add a number 1. We start at the topmost node of binary search tree in order to find additional nodes' proper location. First, we compare 1 and the topmost element, and we see that 1 is less than 15, so it proceeds to the left. Then we compare 1 with 9, and 1 is less than 9, so it continues to the left. Again, we compare 1 with 3, and 1 is less than 3, so it will proceed left once more. But since there is not a node to compare here, 1 is added as a new node, the 3 node, to the left subtree. So the addition of 1 is now complete. Let's try to add a 4. Like before, we start at the topmost node of the binary search tree in order to find the additional node's proper location. We check and we see that 4 is less than 15, so it proceeds to the left. Then we compare it with 9 and the 4 is less than 9, so we continue to the left. Then we compare it with 3 and 4 is greater than 3. This means that we continue to the right. It comes to compare with 8. Since it's less than 8, it will proceed to the left and there is not a node to move from here, so 4 is added as a new node. And this concludes the addition of 4 to the binary search tree. Now let's look at the process for deleting nodes from a binary search tree. As an example, let's try to delete 28. When the node has no children, the target node is simply deleted and the process is complete. Okay, let's try to delete node 8, which has one child. In this case, the target is deleted and the child gets moved to the location of the deleted node, and the process is complete. Finally, let's try to delete node 9. When deleting a node that has two children, the first thing that we can do is to delete the target node, and from the deleted nodes subtree we find the largest node and move it to the deleted node's location. Okay, in this case we delete 9, and from the left subtree we find out that 4 is the largest node in the left subtree, so the 4 is moved to the location of 9. By doing this, we were able to delete a node while preserving integrity of binary search tree. Additionally, if the node was moved also had its own child node, the same process is repeated recursively. Okay, let's continue to look at the process for searching a node within a binary search tree. As an example, let's try search for 12. We start our search at the topmost node of the binary search tree. So 12 is less than 15. We proceed to the left. Here we compare it with 9 and it's greater than 9, which means that we proceed to the right. And here we found out 12. As you see, the binary search tree enables us to search efficiently. However, if tree gets close to the forming a straight line, its search efficiency becomes extremely poor, like a linear search. Okay, here we conclude binary search trees.